Let's review now the criteria for spontaneous activity. We already discussed that when delta G is smaller than 0, it means that it's a spontaneous process. Spontaneous. Could be a chemical, biochemical reaction or another process, but it's a spontaneous process because the free energy Gibbs is lower than 0. When delta G is equals 0, it means that the system is in equilibrium. And when the system delta G is larger than 0, the reaction of the system is non-spontaneous. Needless to say that if you have a reaction that is spontaneous in the forward direction, the same reaction in the reverse direction is going to be non-spontaneous. The most important issue for us today is to discuss the contribution of delta H and delta S for the overall delta G. So you want to do that by analyzing various cases and using the Gibbs equation, delta G equals delta H minus T delta S. For example, the reaction may be exothermic, have a delta H smaller than 0, means a reaction that is exothermic. And the delta S could be larger than 0. In other words, the entropy is increasing. So, in that case, this term is minus T delta S is going to be smaller than 0. Agree? So, if you have this term here is smaller than 0, and this term here is smaller than 0, then delta G has to be smaller than 0. Therefore, this is going to be a spontaneous reaction. Okay, so a reaction that's exothermic and it is increasing the entropy, both factors are favorable. So there is no way, regardless of this temperature, this reaction is going to be spontaneous. The reverse case is when we have a reaction that's endothermic, and a reaction that's decreasing the entropy, delta S smaller than 0. So in other words, entropy of the reaction is decreasing. So if this entropy of the reaction is decreasing, then the term minus T delta S being smaller than 0, this term has to be larger than 0. So now we have here larger than 0, delta G, no matter what, it has to be larger than 0. So this is going to be a non-spontaneous reaction. Okay. Now, situations are more interesting when we have cases like the following. For example, let's say that a reaction is exothermic, but the delta S is negative. An exothermic reaction, that the entropy is decreasing. So from the point of view of if you analyze the contribution of the enthalpy, it's favor the reaction, but the entropy is not favor the reaction. So what matters at the end is the contribution of the overall. So if delta S is less than 0, minus T delta S is going to be larger than 0. So now, one goes in one direction and the other one goes in the opposite direction, right? The two terms of the equation. So it depends on the absolute value of each term. The absolute value of delta H is larger than the absolute value of T delta S, right? Then delta H is going to win, and the reaction is going to have the same sign as delta H. In other words, it's going to be a spontaneous reaction. So this is a reaction that, although the entropy is not favor the reaction is still going. And we discussed this thing in class. This is a reaction that we call enthalpy driven. Enthalpy driven. It means that even if the entropy is not favoring the reaction, the enthalpy is favoring the reaction. If the situation is the opposite, delta H now, the modulo of delta H now, is smaller than the modulo of T delta S, then we are going to have a reaction with delta G larger than 0. Is going to be a non-spontaneous reaction. It will be beneficial to analyze one case, concrete case, so that we can have a better idea of this process. So let's switch pages in here. So let's analyze the reaction 2 NO2 to produce Na2O4. We start this reaction in class, and we said that's an enthalpy-driven reaction. So the delta H for this reaction is minus 57.1 kilojoules per mole, and delta S for this reaction is minus 176 joules per mole per Kelvin. Typically, entropy is a small number, so it's not given in kilo, but rather in joules. So this type of reaction can be spontaneous or non-spontaneous, depend on who is going to have the larger contribution, right? For example, this reaction at let's say 0 degrees Celsius or 273 Kelvin, the delta G for this reaction is going to be what? It's going to be delta H, which is minus 57,100. Remember, you have to put all in the same unit, right? Joules and joules. Minus T delta S. T is 273. And delta S is minus 176. All right, so if you calculate all this thing here, let me use the calculator. You might as well. So I got here negative 9,052 joules per mole, or approximately minus 9, let's redo this thing, minus 9 kilojoule per mole. So it's a spontaneous reaction. At 0 Celsius, this reaction is spontaneous. But if we change this temperature, for example, and conduct this reaction at 100 Celsius, which would be 373 Kelvin, the delta G now is going to be equal minus 7,100 minus 373 now, multiplied by minus 176. Let's plug in this number here in the calculator. as we might as well do over there, and give us 8,548 joules per mole, or delta G equals approximately 8.5 kilojoules per mole. So this reaction at 0 was spontaneous. Now this reaction at 100 Celsius or 373 Kelvin, this reaction is non-spontaneous. So when we have these two factors that are contributing in different, in opposite direction, the temperature becomes an important factor for decision, right? Let's see now the other situation when delta H is larger than 0 and the delta S is also larger than 0. So in that case, minus T delta S is smaller than 0 is contributing favorably in the equation. So again, the same principle. Now delta H modulo, if it's larger than T delta S modulo, the absolute value, it means that delta H is going to win. It's going to be delta G larger than 0 as it is delta H. If the opposite case, delta H, the modulo of delta H is smaller than the modulo of delta T delta S, then delta G is going to become smaller than 0. The reaction is going to be spontaneous. All right, so this is depending on the temperature, because the temperature is going to dictate the absolute value of T delta S. Let's pick up one case here. The composition of ammonia in the gas phase into Na2 hydrogen, nitrogen, and hydrogen in the gas phase. The delta H for this reaction is 92 kilojoules. Kilojoules per mole of nitrogen, okay? Not per mole of ammonia. And the delta S equals approximately 200, but 199 joules per Kelvin per mole of the product, okay? So this reaction at 25 Celsius or 298 K would have what kind of delta G? Delta G would be delta H, which is 92,000, minus 298 times 199. Let's plug in these numbers here and give us 32,698 joules per mole. Per mole of the product, right? So this would be a non-spontaneous reaction that's conditioned. But let's look at this reaction at 250 Celsius. 250 Celsius plus 273 would give us 423 Kelvin. So the delta G now would be 92,000 minus 523 times 199, and we plug all these numbers in the calculator, and now we get minus 2,077 joules per mole, or delta G approximately minus 12.1 kilojoule per mole. So that means we have now this reaction is spontaneous at this very high temperature, but it's non-spontaneous at low temperature. So what is important is that when we have a situation like that, that either delta G and delta H and delta S are in the same sign, either both negative or both positive, the temperature of the reaction is very important. So I hope that's making now crystal clear.